In this screencast, we spent time developing an expression for the total energy of a rigid body. And the reason why we're heading this direction, as you know from particle dynamics, is that we can replace our work in our work-energy relationship due to conservative forces with this term called total potential energy. Now the expression that we see here is for the total energy of a rigid body, because our total energy is going to be composed of the total kinetic energy plus the total potential energy. And the reason why we know this is for a rigid body is because our kinetic energy is split into two parts, where we have the translational kinetic energy, which is the total energy of the center of mass with respect to an inertially fixed point. And then we have what we call the rotational kinetic energy, which is the total energy about the center of mass. And here, our potential energy, we don't have an expression for it, but we do know from single particles is that our potential energy needs to be an expression that is a function of position. So for multiple particles, we can add up that function for each particle, where we have n particles, and so it's our total potential energy is the addition of all the potential energies that are a function of their position vectors. So let's pick up where we left off with our relationship between kinetic energy and work, and then derive an expression for our total energy that's useful for us. Now when we do work on a system, we change the energy in the system. And the relationship that we have so far is that when we do work on a rigid body system, we're changing the kinetic energy. So we've divided our kinetic energy, as we said, into a translational kinetic energy and a rotational kinetic energy. And so here we have the change in kinetic energy, both due to translational and rotational, and then that's equal to the work, which we've said is a translational work, plus the rotational work. And not only that, but keep in mind that these relationships, the work that's translational changes the translational kinetic work directly, and the rotational work changes the rotational kinetic energy directly. So now we consider the types of forces that we have. And we have two types of forces. We have conservative forces and non-conservative forces. And so we've said before that our conservative force is any force in which the work done on the object is independent of the path taken by the object. And that tells us that the only factor that is important in work due to a conservative force is the position. And so by taking only the conservative forces or non-conservative forces, we can separate our work, or we can express our work, our translational work and our rotational work, as the translational work due to conservative forces and non-conservative forces, then our rotational work being the rotational work due to conservative forces plus the rotational work due to non-conservative forces. And so we can rewrite this expression now separated into the translational and rotational work due to conservative forces plus the translational and rotational work due to non-conservative forces. And it's this expression here where we're only considering the work done by conservative forces that gives us our potential energy. And so we have here where we have the change in energy is equal to the work done, and so the work done by conservative forces is going to give us a change in potential energy. So this is a change in the total potential energy, and to make this convenient, we put a negative sign in front of it, because that way we can move it to the left-hand side of the equation and it be part of the total energy where we add the potential energy. So now that we have this expression where it's our change in potential energy, and we're keeping our negative sign here, is equal to our translational work due to conservative forces plus our rotational work due to conservative forces, let's take this system, or take this expression, and turn this into something that we can use. So we've got a rigid body that has a series of conservative forces applied to it. And recall that the conservative forces that we're dealing with in this course are due to gravity and springs. And this series of conservative forces is putting a total force that we express at the center of mass, and it's changing the velocity, or it's contributing to the change, or the velocity that we can take of the time derivative and this being our expression for our work due to a force. And then we also have the rotational component, in which we have these forces due to these conservative forces that are creating a moment about the center of mass, and then we dot that with the angular velocity of the rigid body, and then in this expression for our total work done. And this is where Fg is equal to the sum of all the forces. So here we show forces 1, 2, 3, all the way up to I, located at points I on the rigid body, are equal to the sum of all those forces. And so we substitute this separation of all the forces, or summation of all the forces, into our expression for our change in potential energy. And our first term is pretty simple. We drop in our summation of our forces. This is dotted with the velocity of the center of mass with respect to an inertially fixed point as observed in an inertial reference frame. And then for our moment, we have here that this is our moment due to conservative forces, and then this is our position vector, so it's I with respect to g, which is going to create the moment about the center of mass. So we look at this is r of I with respect to g, and then we're crossing this with the force, the external conservative force that's applied to the rigid body. Now I have no desire to calculate this every time we need a potential energy by finding my conservative forces and then determining all these vectors and dot products and integrals. So let's work with this to find a much simpler expression to use. And we're going to start with our more complex expression and reduce this. And so let's only look at our conservative rotational work, which is this expression. And so here I've rewritten this expression, and all I've done is I've flipped the dot product because it's commutative, where we can have omega before our cross product. And so we have the summation, and we've kept our omega inside the summation of our omega dot with our cross product, which is our moment. And then recall that we have a really useful trigonometric identity. And you've used this several times in this class, and this is from multivariable calculus. And you can see here that when we have an A dotted with a cross product of B and C, then this correlates well with A is equal to omega, and then B as the change or the difference in position vector, and then our C being equal to the conservative forces. And so choosing to convert this into the last form of the expression, we get the summation of our conservative forces dotted with the cross product of our angular velocity and the difference in the position vector with respect, so it's position vector with respect to the center of mass. And because we're dealing with a rigid body, when we look at this term of omega cross our change in position or difference in position, this is the relative velocity of I with respect to g. And so we leave this in terms of I with respect to O, the velocity of I with respect to O, minus the inertial velocity of g with respect to O. And so now we've got a more reasonable looking expression because we've gotten rid of the moment, we've gotten rid of those position vectors, and so we now have this integral of the summation of all the conservative forces dotted with the change in velocity between the point at which the force is applied and the center of mass. So now we substitute this expression back into our original expression, or where we left off, which is our change of potential energy is equal to the translational work plus the rotational work. And now combining all into a single integral, we see that our velocity of g with respect to O cancel out. And this leaves us with this expression, in which the change in potential energy is the work done by conservative forces. And this work done by conservative forces is going to be in this integral velocity form, the velocity of each point at which the conservative force is touching the rigid body. And so what we've done is we've taken an expression that was a translational and a rotational. So recall that we had an angular velocity in there, we had a moment due to the forces about the center of mass. And we've now reduced this into an integral in which we have only the forces and then the velocity of each of those points. And so we can also write this as the path integral of all those conservative forces dotted with dr. And this is of I with respect to an inertially fixed point. And so now with this expression we can apply our conservative forces that we deal with in our systems, which could be the force due to gravity. And so this would be where our conservative force, G, is negative mg, and I'll say that we've got an E2 basis pointing upward, or opposite of gravity. And then our spring force, which we can also put in as negative k, and it's L minus L naught, the change in length from the resting position, and we always call this in the US direction. So this is a vector that can change. And when we plug all these in, we get our normal expressions for our potential energy due to gravity or our spring, which is simply just our mgh, where h is defined as a coordinate that's in the positive E2 direction, and then 1/2 k and then L minus L naught squared. And we've seen this before. So we've taken this rather complex expression for our work done by conservative forces, and this is our total work, which changes our potential energy, and then we've boiled this down into our nice simple expressions for potential energy that we've seen and used before. So in summary, we've come up with an expression for this change in potential energy, where we have our change in, and so this is our total energy of the system, where this is the change in translational kinetic energy plus the change in rotational kinetic energy is equal to, plus the change in potential energy. So this entire side is equal to the change in our total energy of the system. And so this is equal to the left-hand side, the change in our total energy of the system is equal to the work done by non-conservative forces. And this is our translational work, and we also have rotational work. And then we most often express it in this term, where we have the total energy at time 2 is equal to the total energy at time 1 plus the work due to non-conservative forces, and this is where our total energy is equal to our total kinetic energy plus our total potential energy. So you've seen this before. What's new here is, as you know, we have work that's translational and rotational, but this looks very similar to particles. Now, one comment on when we're dealing with a system of particles and rigid bodies, this is the total energy for a rigid body. And when we deal with a system of particles and rigid body, we're simply going to add up all the energies, the translational and rotational kinetic energies, as well as the potential energy for a single rigid body, and that we see here, and then we're going to add those up with all the rest of the particles and all the rest of the rigid bodies. Now, one note about that is that, recall here, we were able to ignore any of the internal potential energy within a rigid body that we did before when we developed our expression for work, because there was no change between the particles. But because in a system, when we find our total energy of a system of particles and rigid bodies, we need to consider that there is work that's done between the bodies. And in our total energy, the conservative work done by springs gives us an internal potential energy that we have to consider and adds to the total energy of the system.